Hi guys, this is Miss Martin, and these are the notes on endothermic and exothermic reactions. So as I talk through these, go ahead and work on making your Venn diagrams. So we're going to break chemical reactions down into two categories, endothermic and exothermic. First, let's look at these words. So the prefix endo means inwards, and then exo means out or outside. And the second part of that word, thermic, just refers to heat, kind of like the word thermometer. So endothermic reactions describe heat going inwards. They are reactions that absorb heat, and by absorbing heat, they cool their surroundings. Exothermic reactions, so heat being released outwards, releases heat and they warm their surroundings. So how do you tell the difference between these two? It depends on if one is cooler and one is hotter than the other, then you know which one is which. Okay, a couple quick reminders. So when we talk about heat, we're talking about a type of energy. So heat is just one form of energy. It's called thermal energy. And thermal energy is considered to not be very useful. Like you can't really use it to do a whole lot of work. You can't really put it to use. But it is a sign of energy being in a system, and it also lets us know that energy is conserved. So now we've come upon one of our main themes for this, and pretty much all of science actually, is the idea that energy is just like matter. It's conserved always. There's always the same amount of energy in this system before and after a reaction, no matter what that reaction looks like or what you have done to it. There's also the same amount of matter in a system before and after. So the idea is that both energy and matter are conserved. The law of conservation of matter, the law of conservation of energy. We have been talking about one without talking just about the other, which is kind of blasphemy because they go hand in hand because they are very related. All right, so here are examples of each one. An endothermic reaction is like an ice cube melting. So an endothermic reaction is cooler than the surroundings. So heat is being used, that energy is being put into the system to melt the ice cube. So the heat has a job to do, it needs to melt the ice cube, and it is going and being pulled inwards by the ice cube, essentially, and that is cooling the surroundings. An exothermic reaction, we have in our example of any time that we have a combustion reaction or a fire, then we know that heat and light are being released and put out into the surrounding environment. So we see heat is going outwards in an exothermic, heat is being pulled inwards in an endothermic. Both of these things require activation energy. Activation energy is the amount of energy required for a reaction to happen. If we think about chemical reactions that we're familiar with, like starting a car or starting a fire, then both of those things, which are really just different forms of combustion, require something to happen in order for what you're looking for to occur. So I can't just spontaneously start a fire. First, I need a match or a lighter. I also cannot just spontaneously start my car. I have to turn my key, which will then turn the ignition and will activate the burning of gasoline. So both of these things are chemical reactions that we see pretty much every day that will not happen without an activation energy. So activation energy is the idea that nothing's going to react together unless atoms or the molecules in them come together. They need to be close in order for a reaction to happen. So this only happens if particles are moving, and how we saw in the IMF Vet Lab, particles don't move unless you put energy into them. So if you want things to be together, you got to use a little bit of energy. You also need more energy if you need to break more bonds and then create new ones. So all of these kind of combine into saying all reactions take energy and some reactions require more than others. If we look at an endothermic reaction, then we're going to notice this. Okay, so I know these graphs are a little overwhelming, but we're going to look at them together, okay? So first thing is that an endothermic reaction needs a constant input of energy to take place. And then exothermic reactions release energy when they occur so they can keep going without any added energy. Both of these things require activation energy, and it's kind of hard to see here, but they actually have the same kind of amount of activation energy. And then also a couple of things happen on an exothermic reaction. The average energy of the reactants is higher and then the amount of the products. And then the reverse is true for an endothermic. So the energy of the products is higher than those of the reactants. So we have to steadily put energy in here to get over this bump, and then boom, it's all kind of downhill. The action can take place and our products are pretty stable. There's energy tied up in them, okay? And then an exothermic process, we're breaking something down. So we have reactants that are pretty high in energy, and we're putting activation energy in, and then we only have to bump up this amount before getting the average energy of our products kind of down here. So we're releasing energy along this way. So you can kind of think of this as like, hey, I have something that's really high in energy. Maybe it's like a food molecule. Maybe it's fuel of some type. And I can burn that, do something, release that energy, and then constantly kind of reaping the rewards here. And then my products are basically like the leftover kind of bits. And then here I'm locking energy away in a product. All right, so just to recap, this is kind of what you should have on your Venn diagram. Endothermic, exothermic. Endothermic, heat is released. The temperature of the surroundings decreases, which means it gets colder, and the total energy of the products is greater than the total energy of the reactants. All of the reverse is true for exothermic. Heat is released, the temperature of the surroundings increases, or it gets hotter, and the total energy of the products is less than the total energy of the reactants. Okay, sorry, there's one more, there we go, graph that I wanted to show that we will probably look at some point. So don't forget also an exothermic energy is released and an endothermic energy is absorbed. So where is the energy going in these systems? In endothermic, it's going inwards, and exothermic, it's being released outwards. So it's kind of the key difference that you should know. And that is it, guys.